agenda for today. We are going to give some motivation and introduction to the problem we are solving. We are going to show our implementation, which will be divided into two parts, one in Golang and the other in Solidity. Then we are going to discuss a little bit about use cases and show our results, compare a little bit with other proposals and some challenges that we faced. And finally, we'll give conclusions and next steps. So the motivation for this work is to solve the privacy issues on Ethereum, because if you have a smart contract and if the input data for this smart contract is a private data, then you have a problem because everybody is going to see your input. Then you need some kind of encryption to protect your data. One possibility is to use trusted execution environments to protect your data so that you put your data into a special hardware that you know that only inside this hardware it will be decrypted. But this is not so simple. There are many attacks in the literature. For example, for SGX, it's possible to attack the platform and obtain private information. Another solution is to use cryptography, and in particular zero-knowledge proofs, which is a technology that's gaining traction for blockchain. In summary, zero-knowledge proofs allows you to prove a certain statement about your data. So you don't want to reveal all your data, you just want to show that your data respects some property that's enough to validate what's necessary to validate for blockchain. So we chose Bulletproofs because it was specifically designed for blockchain, and it's considered one of the best alternatives to construct private transactions. Zero-knowledge proofs is not a recent technology. It's basically 30 years old, but now it's gaining traction, but it's a somewhat old technology. And one important thing is that it's being standardized. It started last year in Boston. They started discussing how to standardize zero-knowledge proofs, and Bulletproofs had a lot of attention. And also, it's important to know that others are also trying to construct Bulletproofs. For example, Monero released it last year, and also Corda is experimenting with it. So, an introduction to zero-knowledge proofs. Imagine you have two parties. In cryptography, we used to call them Alice and Bob. They are talking to each other, and Alice wants to prove that her data possesses some kind of property. So Alice is going to send a couple of messages to Bob. Bob is going to return some challenges, and after this communication, Bob will be hopefully convinced that the property is indeed valid. And we have three properties for this zero-knowledge protocol. The first one is completeness. So if the property is really valid, always it will succeed. So the protocol is always going to work if the property is valid. And if the property is not valid, then what is going to happen is that Alice is trying to cheat, but the soundness property tells us that it's hard to cheat. So if the property is not valid, after this protocol, Bob, with high probability, will not be convinced that this property is valid. And finally, the most important property, which is zero knowledge, we have that Bob doesn't know anything about the secret, so he learns nothing about after the protocol, and it's hard to define this mathematically, but there is a way to do that, and this seems like magic, but it's possible to do this kind of thing and prove that no information was leaked from your secret data. But in the context of blockchain, we don't want this many interactions. We want just a non-interactive transformation that we can apply to the zero-knowledge protocol, so that Alice is going to generate a zero-knowledge proof offline. It could be offline, and this zero-knowledge proof can be posted to the ledger, and then Bob can read this zero-knowledge proof, and also offline can validate the zero-knowledge proof. So we want to avoid this online sequence of messages. And also we would like to have a zero-knowledge proof of knowledge, because only zero-knowledge we are proving that there is a secret respecting some property, but with proof of knowledge, we prove to Bob that we know one of these possible secrets that respect this property. And this is a little bit harder than just zero knowledge. In particular, we are interested in a specific flavor of zero knowledge, which is called zero knowledge range proofs. This allows us to prove that a certain secret number belongs to some numeric interval. So for example, imagine that we want to prove that someone's age is between 18 and 300 without revealing the exact age. So using zero knowledge proofs, we can solve this problem. We generate a piece of data called zero knowledge proof, and we send it to Bob, and Bob can run an algorithm that will return to us true or false, and it will correspond to this property of being between 18 and 300. And there are some ways to do that, and some categories of solution to this problem. The first one is called square decomposition. We show that the secret can be decomposed into square numbers, so it must be positive. And if we can show that some secret number is positive, then we can use a mathematical trick to have a generic interval. And another flavor of range proof is called signature-based. And this flavor works by having digital signatures over all the numbers in your interval. For example, all the numbers between 18 and 300 are going to be signed. And we use a blind signature scheme to show that we know one of these values, so that Bob is not going to understand which number was signed, because it's a blind signature. Another strategy to solve this problem is called multi-base decomposition. In particular, the bit decomposition is the most simpler solution, where you decompose your secret into the bit decomposition, and you show that this is valid. You show that the summation of the bits are going to correspond to your secret, and you show that each bit is indeed a bit, 0 or 1. And this is a basic strategy, and we can use not only binary decomposition, but general basis, so that we can have more efficient schemes. This one is used in many blockchains as an old solution for range proofs. And now we have bulletproofs, which is part of this strategy, but I separated because it's the focus of the presentation, but it uses the bit decomposition to show that we have a secret in this interval. But this bulletproofs is much more efficient than this scheme here. So bulletproofs, as I said, is an efficient solution for zero-knowledge range proofs. It was specifically designed for blockchain. It allows not only range proofs, but it allows us to prove any possible statement. And what I mean by this possible statement is any computable algorithm which will return true or false. So it's a decision algorithm. For example, if you imagine a sorting algorithm, it's not a decision algorithm. A sorting algorithm must sort some array, but we could imagine a decision sorting where you give an array to the algorithm and it returns true if this array is sorted. So bulletproofs can can generate zero-knowledge proofs for any possible decision algorithm. So it's very powerful. we can use bulletproofs for many other applications beyond range proofs. And one important characteristic of bulletproofs is that it is not dependent on the trusted setup. All others previous constructions of range proofs depends on this trusted setup, which means that who generates the parameters for the scheme must be trusted, because there is a trapdoor, there is a secret that if the guy that generates this secret keeps that, then he will be able to generate fake proofs. So, for example, Zcash uses a scheme that needs a trusted setup, and this is a problem till today, because people want to know how the secret was thrown away, because it must be destroyed. Otherwise, if you have this, if you possess this secret, you can generate money out of thin air. If this setup is compromised, as I said, this may have very serious consequences. So we don't want to have this trusted setup. There is another technique, a cryptographic technique to solve this problem, which is called multi-party computation, but it's even more complicated than zero knowledge, and we would like to avoid using more cryptography to solve this problem. And bulletproofs, by design, doesn't depend on the trusted setup. So ZK snarks and ZK starks are two technologies that are being getting famous in the context of blockchain, because they allow us to generate these generic zero-knowledge proofs. And now we have bulletproofs as another technology that has advantages and disadvantages when compared to ZK snarks. Our implementation started with Golang, so implemented in Golang over the Go Ethereum library. In order to avoid the trusted setup, we need to use a hash function, and we call this strategy a map to group, so that we use a public string. Everybody knows this public string, and we hash this public string to generate all the parameters of the zero-knowledge proof scheme, so that there is no secret anymore, and you don't need to throw away or destroy any secret. You just use this public string as your main parameter, public parameter, to generate the others. So this is the way we solve the authors of the Bulletproofs paper solved this problem by using this strategy. And this map to group means that we are going to use the hash function to map to the elliptic curve, and then you can generate the parameters. So it's impossible to break the scheme, given that this hash function is one way. So a hash function we believe that these hash functions are secure, because we don't use that only for this purpose. Everything in blockchain depends on the security of the hash function, so we are already believe that this is true, so this is not a problem. And we use this elliptic curve, which is the same as in Bitcoin, and this is it's important to choose a good elliptic curve, because the performance will differ if you choose a different elliptic curve. And we are not yet using two possible optimizations of this Bulletproofs implementation, which is called multi-exponentiation, and the other is called aggregation. Multi-exponentiation allows you to compute many multiplications over the elliptic curve in parallel, much faster than doing all the multiplications separately. And aggregation allows you to compute many range proofs using just one piece of data, one data structure. You can aggregate many range proofs, and this is very important for many applications. And after that, we implemented the verification algorithm in Solidity, so that we can generate the zero-knowledge proof offline, post it into the ledger, and use a smart contract in Solidity to verify if it's true or not. Um, there is another implementation of Bulletproofs in Solidity. It's called BulletproofJS. All those references are in the end of the presentation, so that you can check later if you want. But this implementation is using a different elliptic curve. This elliptic curve is called BN256, and it's an elliptic curve that is used to compute bilinear pairings, which is a more complicated thing, and we don't need that. And the performance of this elliptic curve is not that good, so we decided to implement our own version using the same elliptic curve as we chose for the Golang implementation, and we hope to see a better performance. And in order to have operations over the elliptic curve, we use Vitalik streak to be able to have multiplications over the elliptic curve. And Vitalik claims that this is 25% of the cost of using BN curve. So we hope to see an improvement in the performance just by exchanging one elliptic curve for the other. BulletproofJS, the other implementation, is not using yet the multi-exponentiation optimization, but they are already using aggregation. So this is an important optimization, and we plan to implement it too, but we still don't have it. Now I'm going to discuss about some possible applications. One possible application in the context of DLT, I would like to emphasize 3 possible applications. One is confidential transactions, where you can protect the important information in some transaction, for instance, the sender and the receiver, and the amount. Range proofs is important to protect the amount, also known as the denomination of the transaction. If you use regular transactions, you know the amount of the transaction, you know the amount being transferred from one party to the other. And if you use zero knowledge, you can encrypt the amount, but still be able to prove that the transaction is valid. What you need to prove is that the amount is positive. Otherwise, the transfer is in the opposite direction. If you use a negative value, then instead of transferring money to another party, you are stealing money from the other party. So it's very important to have range proofs to show that the secret data, which is the amount, is a positive number. Another application is Mimbo-Imbo, which is a proposal to use aggregate transactions to optimize the confidential transactions. So since Bulletproofs offer this aggregation of range proofs, it's perfect for Mimbo-Imbo. And for example, if you use normal range proof, it would take 170 gigabytes to have the total storage of the blockchain. But if we exchange the old range proof for the Bulletproofs, then we can have the same solution with 16 gigabytes, so basically 10 times shorter storage. And one comment here is that Mimbo-Imbo is a magic word from Harry Potter, and the author of this paper is also a character of Harry Potter. In particular, I don't like this kind of thing, like Bitcoin have the Satoshi Nakamoto, and I don't like these things that are hiding the real people that is producing this knowledge. I prefer to have a transparent proposal. Everybody knows who is proposing what, but that's just a comment. Another application is called provisions. And in this application, we want to construct an exchange that is solvent. So you have your cryptocurrency in this exchange, and the exchange proves to everybody that it has enough funds to give back all the cryptocurrencies to each individual. So it proves that it's solvent, that it has enough funds. And it's possible to have a huge optimization here if we exchange the old range proofs for the new bulletproofs. In particular, it's 300 times faster solution just by replacing the range proof. Another kind of application that we are going to discuss is the generic applications that doesn't depend to be working in the blockchain, but can work in the blockchain, there is no problem, but can be in other contexts. For example, we can use range proofs for KYC to show, for example, the age of someone is over 18 and can, for example, consume some service. Another application is anti-money laundering, so you can prove that the participants in some transaction are not, for example, in some blacklist of companies or countries that are doing money laundering. So a similar application is reputation validation. You can, for example, check if some country or company is not under embargo or sanction or whatever. So you know that you are doing business with the correct party and you are not doing the wrong thing. Another interesting application would be common reporting standard, which is a standard to automatically exchange information from financial institutions. And since this is automatic and it's a generic solution that allows you to use for different kinds of data, you need a generic zero-knowledge solution. So you are not going to use only range proofs here. You need to use all the power of the bulletproofs. You need to use all the possible different zero-knowledge constructions that bulletproofs allows you to do. And finally, electronic voting is very important nowadays. You can prove that the voters voted correctly and the final summation of votes were computed also correctly without exposing individual votes. So you encrypt individual votes. You can the government can sum up everything and prove to everybody that it was computed correctly. And also electronic auctions, where you want to propose bids, and the highest bid is going to win. Or the opposite, an electronic procurement, where you want to find the lowest bid. So, for example, if some company is trying to find the best service provider, then this company can open an electronic auction to see who is going to offer the lowest bid. And we can have privacy in this context by using zero knowledge. In particular, we are going to focus on the electronic auctions, and we are going to use a simple solution. There are others in the literature using more complicated protocols for electronic auctions, but we started with a simple construction to use more range proofs and test out our solution. The idea is that the auctioneer publishes a public key for an encryption scheme, and the seller is going to publish the details of the item, the minimum value R, and the time t to end the bidding phase. And each bidder, I, commits to his bid, BI, and this commit is a kind of an encryption scheme. It's going to hide the information that is inside this commitment. And we are going to use zero-knowledge range proofs to prove that this bid, BI, is in the interval between R and max for each I. And after time t, each bidder encrypts under PKI the bid BI and the randomness used to generate the commitment, which is RI, and every party is going to send this information, this encrypted information, to the auctioneer. Then the auctioneer decrypts those values and validates that the commitment is valid. And he is able to open these commitments to be sure that it was correctly computed. And with everything now in the clear, the auctioneer can detect the winner, the winning bid, and then the auctioneer can use zero-knowledge proofs to show to everybody else that this result is indeed okay. So he must use zero-knowledge proofs to show to all the losers that their bids are between R and the winning bid minus 1. Now I'm going to show some results. We measured the gas consumption, but we are refactoring the code. So this is a preliminary result, just to show that indeed replacing the elliptic curve seems to be a good way, but we would like to see the result after the refactoring. So just a preliminary result. This is the next slides are going to show more important information. But indeed, it seems to be faster. If we compare bulletproofs with other range proofs, here we are seeing all possible strategies to construct range proofs. And here we have bulletproofs is better than all the others. So, and this is a logarithmic scale, so it's supposed to be much better. This is specifically for the proof size. We also measured the complexity of the prover algorithm. So we have that now it's not the best for all situations. For this secret size, so it depends on the range of, size of the interval, then there will be another scheme that's faster, but this is very short. This is just a couple of bits. So if this is not the situation, if we are in this part of the graph, then bulletproofs is going to be faster. But in the context of blockchain, we are not so interested in the prover complexity because this is going to happen offline. We are interested in the verification algorithm because all the nodes are going to run it. So for the verification complexity, we have, again, that bulletproofs is better than the others. And for bigger secrets, this difference is huge. So bulletproofs is logarithmic. The big difference is that the proof size is logarithmic with respect to the range size. So it's more efficient in theory, but also in practice. And some timings for a specific size of the secret, we measure the time for all those construction. In our GitHub, we have these implementations, the Budo implementation, the signature-based implementation, and bulletproofs. And this one is an implementation from another group that was done in C. It's faster because it has the multi-exponentiation and the aggregation. So we can see here that there is a big difference between those lines. So we can see that with bulletproofs, we have a faster solution, especially when we see this last column for the verification. We see that we can run much faster verification using bulletproofs. Some challenges that we faced. We had to adapt the Golang Ethereum implementation of the elliptic curve to have some auxiliary functions. It was not that hard, but we didn't use the exact code that was there in Go Ethereum. We had to change it a little bit to deal with the point at infinity and some particular mathematical properties that we had to check. And also we had to provide the same interface as the other curve, the BN curve. And in Solidity, we faced some problems trying to estimate the gas consumption. So that's why I don't trust completely the table I showed you. We are now refactoring the code, as I told you, to improve the gas consumption. And also a small detail in the beginning, the string concatenation, because we need this thing for the hash function, and the the string concatenation from the Golang code was not matching the string concatenation that was available in Solidity. Then we discovered a simple trick to solve this problem, but it took some time. We also had some problems with Truffle. It was giving us a strange error, and we've discovered that it was a problem in an old version of Truffle, but now it's supposed to work, but we'll have to adapt our code to work with a newer version. But basically that's what we faced. And some conclusions. Although we can use hardware, special hardware as TEs, trusted environment execution environments, we don't want to do it always. There are many possible problems that we can use TEs, but cryptography is better exactly because we don't want to trust the parties. And we are interested in blockchain and DLT because we are in the context of dealing with different parties that don't trust each other. So cryptography is the best solution when we have this kind of problem. But if there is no trusted setup. And that's why Bulletproofs is very interesting to solve the privacy issues of blockchain. And it seems to be a natural choice for this kind of problem. And many new ideas are being proposed recently. It's being optimized in the academic works. Many new research is appearing to optimize zero-knowledge proofs and the standardization effort that I told you. So that's the moment to study and implement zero-knowledge proofs. Since it was specifically designed for blockchain, it allows to generate very short proofs, which is very interesting. But the Solidity implementation is slower than the Golang implementation, so actually we are not sure the role of the ledger. If we should validate the zero-knowledge proof, it depends obviously on the application, but if you could validate it offline, maybe, at least for this moment, it would be maybe better. So a question for the audience is that if you think that the verification of zero-knowledge proofs should be done off-chain, because you could use the ledger just to post the zero-knowledge proof, and the validation can be executed offline, since it takes much more time to do it online, and every node must do it too. And as next steps for this effort, we want to optimize our implementation using the multi-exponentiation and also the aggregation. We want to explore more applications and use cases. We want to explore also the possibility of generating other zero-knowledge proofs, not only range proofs. So we want to go the way zk-snarks and zk-starks are going. One difference between zk-starks when compared to zk-snarks is that it is post-quantum. And it's important to have this property because some estimations says that the post-quantum cryptography must be available till 2025. So we have 6 years to prepare for the quantum computer. So it will be an important question for the next years. And also multi-party computation is very interesting because it solves the even more generic problem of doing zero-knowledge proofs among different parties, because the common zero-knowledge proof that I showed you is just for one party that has his own secret, but if many parties have different secrets, they could execute a protocol called multi-party computation to generate an equivalent of the zero-knowledge proof, but as a result of this protocol, and everybody is going to be able to check if it is valid or not. And here some references that I used. And now open to questions, comments.
So, what are the benefits and drawbacks of using the Bitcoin curve against the BN256 for your application?
The difference is the performance. It's for blockchain, specifically Ethereum, it's supposed to be 25% of the cost of BN. Because BN is supposed to be used in the context of bilinear pairings. So for example, aggregate signatures, ring signatures, group signatures, this kind of stuff is important to have bilinear pairings. But here we don't need bilinear pairings, so there is no reason to use this curve BN. It's not as fast as the Bitcoin curve.
So what are the drawbacks? Because you cannot get always benefits, right? What are disadvantages?
This curve is the Koblitz curve, and it was not standardized as the other curves that are being used not in the context of blockchain. So people don't understand how the parameters were chosen. This is one drawback, but there is a lot of discussion about using this technology. No attack is known, so although there is some doubts, no one was able to discover a way to explore it.
So do you have security proof and also any formal verification of your approach? Because that might be going to the application for financial companies, right? So a lot of money at stake. So are you going to invest some on the security proof and the formal verification?
Yeah, for now, no. We are just exploring and doing a proof of concept, but this effort is going to continue, and probably at some point we will have more mature solution, and maybe we should follow this path, yes, but for now, no. First, we are going to focus on optimizations and the organization of the code itself, the security of how we protect the keys, and etc., to have a mature solution in the context of cryptography, and then would explore this kind of things.
So in ING, what applications do you have for blockchain and bulletproofs? And is it just in development or in production already?
Not in production. It's just to understand better how the protocol works. It's not in production. It's not ready for production. The code is in our GitHub. We actually need help. If you want to help us and participate in this effort, you are welcome. But it's not ready for production yet. But we are looking for concrete problems at ING that could benefit from this implementation. So now that we've finished the basic implementation, we are going to study possible problems to apply this solution. So there are possible problems, as I showed in this slide, basically here. These are some possibilities of application of range proofs and also more generic zero knowledge. For example, this problem is very interesting, and anti-money laundering is also very interesting, and the KYC is very important for the bank. So these are possible ways to apply this technology.
Once again, what was common reporting standard?
This is a standard that is being applied nowadays to exchange automatically information from financial institutions to be able to validate generic properties of the market, so that you are not going to do business with some party that you are not supposed to do business with. And for example, it's similar compared to anti-money laundering, but it's not focused on this application, but it's also dealing with this kind of problem. But you could use it to validate this information in a generic way. It's not focusing on a specific problem, but it's you define your own schemas to describe what data you are transferring to other parties, and then you describe which kind of validation you need to carry over your data. So it's very generic, but since it's very generic, the best solution to have privacy of this data, if you are transferring private data, is to use zero knowledge. Because it's very generic. You can define your set of data that's going to be sent to other parties, and probably you are going to send some private data together.
Just one question. In the case of privacy on Ethereum, verifying a transaction denomination is greater than zero is not we want to be sure as well that below your account balance, and you want to have it encrypted. So is it possible to have this kind of range proof against encrypted range? And maybe using some kind of homomorphic operation to perform like the subtraction.
Monero, for example, is using homomorphic encryption. And you can use, yes, you can encrypt using a homomorphic encryption scheme. And using this scheme, you can add amounts. So that's the way Monero is solving this problem. They are also using ring signatures and other primitives, but the way they protect the amount is by encrypting it using a homomorphic encryption scheme. So yes, it's so I maybe should have added homomorphic encryption in the list in the end as a possible next steps, because indeed homomorphic encryption is very interesting here. So I could say that homomorphic encryption and verifiable computation are also two possible ways to explore further. Verifiable computation is similar to zero knowledge, but has no zero knowledge property. You can verify the computation, but there is no guarantee that information is being leaked, but it's already interesting. It's a little bit less than zero knowledge, but it's useful. And homomorphic encryption is interesting because it allows you to have arithmetic over the data you are. So it's very powerful. And
so how long did it take you to reach this stage, and how many people were you working on this project?
Basically, me and Alexey, we started, I think, in August. And the Golang implementation finished in October. And then I waited a little bit before implementing in Solidity. I started the implementation in Solidity, I think it was almost December. So we are still finishing the details on the Solidity code, but it's ready. It's working, the math is working, but we need to improve the code. Yeah.
So for your outputs, do you have like a zero value outputs? Because like, let's say one have some blinding, not all outputs are like positive.
I don't know if I understood.
So you have like a range proof actually like input and output, right? That's the context of the transaction. You have like positive inputs and support positive outputs, right? Like Bitcoin transaction. So do you have like a zero value outputs just for the blinding?
You don't know if the input is positive or negative. You are claiming that it's positive.
Yeah, but do you prove that's positive? But I said, do you have like, can you output with zero value output? So
Yes, there is zero knowledge proofs to show that your secret is equal to a certain value. But in many applications, it's not going to be useful because it's showing to everybody the value. It's equal to zero. So in many applications, it would be useless to have an exact value for your secret. But in some contexts, it's useful.
like a ZK aspect right there implemented in the Solidity as well. So they also have the positive and zero value outputs.
Yes, in particular, the zero value is very useful. But you reveal all the information about the secret. But if it's part of a more complicated protocol, it's very useful. Maybe if you are running, I don't know now an example, but it's useful to have this comparison for exact values. But you need to take care, because if you are showing with a zero knowledge proof that something is equal to zero, in general, there is a question why you are using zero knowledge, because you now know the value of the secret. But in some contexts, I know it's useful, but I don't have a specific example now.
So if we have like a custom problem or a circuit, is there an interface already? I think the original Bulletproof software had the Pinocchio
Pinocchio is really interesting. We are reading and studying it, but for now, no exploration in this generic zero knowledge. Pinocchio is a solution for the verifiable computation, and it can be transformed into zero knowledge. And there is a compiler, and this should may be the path to follow to have the generic solution for bulletproofs. But we will need to have an extra layer to compile from Pinocchio to bulletproofs circuit.
So is there like a specific bulletproof circuit format to also write one constraint?
Yes, it's a little bit different because the building block is an inner product, and it's totally different from other proposals. So you need to compile the arithmetic circuit to inner products. There is an implementation of this compilation in Java, and this is from the authors of Bulletproofs paper. I played a little bit with this code, so it's a good starting point.
But in theory, it should be possible to convert whatever this outputs to basically have it verify Ethereum.
Yes. In theory, yes. It's very complicated, a sequence of compilations, but yes. With no trusted setup.
Thank you for your presentation, very interesting. Is it possible to say anything more about Bulletproofs verifier? Is it computationally or financially cheap or expensive to run? And how does that fit within the overall system?
So the verification plot is here. It's much more efficient than other alternatives for range proofs. But for the general case, it's also supposed to be efficient because it's logarithmic and the proof size is short. But I don't have concrete numbers to show you. But since it was designed to have short proofs, in the context of blockchain, it must be one of the most interesting solutions, yeah. But it's much better than others because this is like from here to here, it's like 100. So it's 100 times faster, actually more than that, almost 1,000 or more than 1,000 times faster than the other one. There they square the decomposition. For many different size of secrets. So here it's the size of your secret. If you have a secret of, I don't know how many bits, here are the number of bits of your secret. So it will change the performance. For example, this one is exponential. So this is going to change after a little. But at some point, for very, very, very big secrets, this one is going to be faster. But the size of the secret is like 2 to the 500. It's huge secrets. And it's not practical situations. Maybe, I don't know, if you find some interesting application that whose size of the secret is so huge, then yes, you could use this one because at some point this would cross. But for small secrets, Bulletproofs is much faster.
All right, well, let's thank Eduardo for.
Thank you.
We'll just have like a quick 5-minute break, and I'll run through the.
Is this your jacket? Yeah, just want to take the computer. No problem.
Istituto ING DLT